So in the next series of videos here, I'm going to be introducing you to our next big theorem. We've had the intermediate value theorem, which says if a function is continuous on a closed interval, then we must hit every function value between the endpoints. And the extreme value theorem, which says that if a function is continuous on a closed interval, then there must be an absolute maximum and an absolute minimum. The mean value theorem is actually a pretty deep one for us. There's a lot of things that are allowed to happen because of this, and they're not all very obvious as to why they're connected to the mean value theorem. So in this video, I'm just going to talk about what is the mean value theorem and when can we use it. And then the next series of videos, I'll start going through examples and concepts that build off of this theorem. So the mean value theorem, or MVT, like our other theorems, it's really, really important that we pay attention to the hypothesis because we have to show that we're allowed to use the theorem before we actually use it. So the hypothesis of the mean value theorem says that I have to have a function that's continuous on a closed interval and differentiable on the open interval. So we have two things we have to check here. I have to be continuous on a closed interval and differentiable on the open. So if I'm saying that here's A, here's B, from here to here, including the endpoints, I have to be continuous. And from A to B, not including the endpoints, has to be differentiable. And I can see that I have a smooth continuous curve from A all the way to B. So the hypothesis is met. The conclusion says that when I have those conditions, there has to be some place in between A and B, inclusive of A and B, such that f prime of C is equal to f of B minus f of A. I will admit, I don't remember it in terms of this. I think of this in terms of slope. So f prime is the derivative, and another name for the derivative is the slope of the function. And then f of b minus f of a over b minus a is our old school slope, which is the slope of a secant. And sometimes I'll say slope of a tangent instead of slope of a function for the f prime part. So what this is saying is, if I find the slope between my two endpoints, the MVT guarantees that somewhere between A and B, there's at least one point where if I draw the tangent line, it's going to be parallel to that secant line that connects A and B. And so I could say, well, it looks like there's going to be one point right about here where the tangent is parallel, and it looks like one point right about here. Much like the IVT and the EVT, it doesn't tell me where it happens. It's just telling me that it has to exist. And if it's guaranteed to exist, then I am sometimes interested in finding out where does it happen. So then just some quick examples to talk about, am I allowed to use the MVT? So I'm going to first run through a graph of f of x, which is just a nice absolute value function. And then I'll go through g of x. So if I look at the closed domain from 0 to 4, so 0 to 4, my function is continuous from 0 to 4, but it is not differentiable. So the MVT does not apply. If I then look from 3 to 5, from 3 to 5, my function is continuous and differentiable because the corner is not in that interval. So the MVT does apply. And then if I look from 2 to 5, here's 2, here's 5. It is continuous to 2 to 5. And it is differentiable from 2 to 5, and the question then comes, well, but the corner's at 2. But remember, for differentiability, I need the open interval. Since the corner is at 2, from the open interval from 2 to 5, my function is differentiable. So yes, the MVT applies. If I do kind of the same idea over here on g of x, from 0 to 4, my function is not continuous. So I don't even bother checking differentiability. The MVT does not apply. If I look from 3 to 5, my function is continuous from 3 to 5 because the discontinuity is outside of that interval. And it is differentiable from 3 to 5, so the MVT does apply. And then if I look from 2 to 5, my function is actually not continuous. And this is different because for continuity, on F, the fact the corner was at 2 was okay because differentiability is on an open interval. My discontinuity being at 2 is a problem for the MVT because my continuity has to be on the closed interval and include the endpoints. So this is not a continuous function from 2 to 5, so the MVT does not apply.